All right, so a couple of quick things announcement-wise. First, if you're a senior, this is the last class period that I will see you and the last class period that I expect any work. And I still feel like the bargain that I have put forth is reasonable. I hope it seems reasonable to you, and that bargain is, if you use your class time to try to learn, I'll give you full credit. And if you don't do that, then it gets a little weird, because I don't want to be a jerk or anything like that, but philosophically, and you all know, like, I am sort of a philosophical person when it comes to this stuff. I think it's important. I think it's important to be able to say things like, if we say we're going to do something until a certain date, let's do it until that date. And not say, like, oh, there's only a week left or only 2 days left or whatever, and then quit early. Like, we don't have to do that. And even more importantly, I would like this in general to be something that we look forward to. I would love for school to be something where we're like, hey, this is cool. There was a dude in here earlier today who is, you may see him at some point before the end of school. He's just doing some observations, and he is a reproductive biologist. He's like, has a PhD in biology. He studies the human reproductive cycle, and we're talking about simple harmonic motion. And so he's back there, he's just making observations. He's going to go into a teacher education program starting this summer. Super nice, super smart, super interesting guy. And I'm talking about oscillations, and he's like a reproductive biologist. And when I stopped talking, I went back and I was like, haha, I'm sure you knew all this stuff, and it probably rings a bell, but it's probably been a while since you've done physics. And he was like, well, actually, yes, it has been a while since I've done physics. I'm rusty on the math, but when you talk about oscillations, that's my job. Because if you look at hormone cycles for both males and females, when it comes to reproduction, it's oscillations. And he even told me, for females, it's more like spikes. Females, it's like low, 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 boom. Low, 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 boom. For males, it's more of a simple harmonic motion kind of thing. And those kinds of things are interesting to me. I'm going to talk about some stuff as we get closer to the end of the period, or to the time where you're going to start working. I'm going to talk about some stuff that I actually looked into because I find it interesting. And I wish that all of my students had the same approach, because it's fun. Not because I think I'm better than you or I think you could be better than me, but just because it's kind of fun to be interested in stuff, and it's not that hard. Okay, so that's thing one. Thing two is if you have a book, a physics book, you can return that. We're not going to use that anymore. And if you have a Chromebook, but you don't need it for your other classes, it is not going to be required in here. I am going to ask you to, like, you're going to need access to the internet at some point. You're going to need to, like, turn stuff in. But if you have a phone or a tablet or a laptop or whatever, you don't need your Chromebook just for me anymore. You can, for the rest of the year, you can get by with a minimal amount of technology. So if you'd like to get rid of some of that stuff, knock yourself out. And then for those of you who aren't seniors, the way this is going to look is today is going to be the last new information, and for the rest of the year, your job is going to be to do something that demonstrates to me that you understand what we have been doing. So part of it is going to be learning stuff, because there's probably some stuff that you don't understand, but one difference between the work we're going to do with simple harmonic motion and the stuff we did with both rotation and work and energy is that I'm actually going to ask you to collect data and make a prediction and then test your prediction and then evaluate it. So it's not going to be just tell me what you're going to do and then turn that in. It's going to be tell me what you're going to do and then do it and then turn that in. The grading will look the same. If you show me that you are trying to figure stuff out and trying to learn stuff, if you are in here during class and you're working and you're collecting data, then at the end of it, if you end up not being able to answer the question that you asked, or if your data collection crashes and burns, or you can't even get your system up and running, that's not going to be a problem. I'm not going to make you come in outside of class over the summer, but what I just want to see that that drive to make the most out of the class period, and ideally it will happen in the context of something that you personally find interesting and rewarding. Okay, so any questions about any of that? Okay, so we are going to look at the mathematical underpinnings of the connection between simple harmonic motion and rotational motion today. And there's a couple of things that we're going to do. The conceptual part of it involves this idea. If we have an object that is moving in what we call uniform circular motion, so there's a constant angular velocity and no angular acceleration, then we have an object that is moving in 2 dimensions, right? So that's our rotational circular motion that looks like this. This is 2-dimensional motion. This is not really an oscillation per se. This does not involve a restoring force. This does not involve any one particular equilibrium position. And so it's not really simple harmonic motion. But what's really cool about this is that if we take circular motion and we break it into 2 axes of 1-dimensional motion, then what we're going to see is one axis which just moves up and down, and one axis which just moves left and right. And the motion of this object along its circular path, if we look at it one axis at a time, each of these axes will exhibit simple harmonic motion. And you'll see a video of this in just a second, but effectively, when we have an object moving in a circular path, and we look at only the vertical component of its motion, it goes up and down. As it gets closer to the top, it slows down vertically. As it gets closer to the bottom, it slows down vertically. And then as it gets closer to the middle, it speeds up. So its circular motion looks like this. The vertical component of its circular motion looks like this. And the horizontal component of its motion does the same thing. It slows down at the extremes, and it speeds up through the middle. That's simple harmonic motion. Conceptually, this is what I want you to understand. Mathematically, we have equations that we can build that will tell us about the left and right component and the up and down component of an object that's moving in a circular path. Since the one-dimensional motion of an object undergoing circular motion will be simple harmonic motion, we can use the equations of rotation broken down by dimension to effectively model simple harmonic motion. Those equations are complicated, and that's the piece that I don't expect that you're all going to understand. Some of you will. All of you have the capacity to do it. For some of you, there's just not going to be enough time. And then there's another piece here that we're not actually going to get into that much, and that is kinetic and potential energy in simple harmonic motion. I'm going to talk about it for about a minute. Some of you, though, will choose to investigate this in more detail down the road, and you're welcome to do that. So what I want to start with is to have you all make some sketches. And the sketches are going to be of position versus time, velocity versus time, and acceleration versus time, which is proportional to net force. And here's what I want you to think about. We have some information about simple harmonic motion, what these things should look like, and some information about kinematics. So here's what I'm talking about. If we go back in time and think about when we were looking at position, velocity, and acceleration versus time graphs in kinematics, then what we saw is that our position versus time, velocity versus time, and acceleration versus time graphs were connected to each other mathematically. And when we had constant acceleration, they were connected in a very simple way. if we, for example, and the starting conditions matter, we could have a whole variety of starting conditions, but if we were to start with a positive acceleration, a velocity of 0, and say a negative position, and then I were to tell you that we were going to have constant acceleration, you then could predict that the acceleration versus time graph would just be a straight horizontal line. The velocity versus time graph would be a diagonal line going up. And the position versus time graph would be a part of a parabolic curve that, you know, increased in slope upward, an upward facing parabolic curve. And the reason, this is true even when acceleration isn't constant, but it becomes really predictable when acceleration is constant. And we talked about the reason for this being that at any one time, the acceleration of an object is equivalent to the slope of a velocity versus time graph. And the velocity of an object is equivalent to the slope of a position versus time graph. So having any one of these graphs allows you to draw the shape, at least, of the other two. You may not know the starting point, but you can create the shape. So what I want you to do is the same thing, only I want you to do it for simple harmonic motion. And I'll start you off here because there is something that we know, and that is for simple harmonic motion, what does the position versus time look like? What's the shape of that graph? Anybody remember? It's a sine wave. Yeah, so Caleb says,
It's technically the opposite of a curve.
yeah, and so that actually what we can say for sure is it will be sinusoidal. Okay, it's a sine wave, but it is not a sine function necessarily. It might be, or it might not be, and we'll talk about that in a little bit more detail, but effectively what that depends on is what is our initial position and what are our directions, what is the frame of reference. By convention, we typically say that when an object is undergoing simple harmonic motion, it starts at its maximum positive position. And that means that the rest of the motion will follow a cosine function. It'll be a cosine curve. It will have a maximum and a minimum and an equilibrium position at 0. The maximum we refer to as the amplitude. And so the maximum is positive A. The minimum is negative A, and we get this sine wave that explains the position versus time of an object undergoing simple harmonic motion. So my question to you is, based on this, what will the position and acceleration versus time graphs look like? And you might know, you might be able to say, oh, well, I looked that up in the book, and it's this kind of a wave and this kind of a wave. Or you may just remember it, or you may be able to do the calculus. But what I want you to do is, regardless of whether you know it already or not, I want you to think about this whole slope thing. Because it's possible to, just by thinking about the slope, figure this out. You don't need to know any calculus, you don't need to know any trig even. All you need to be able to do is identify the slope on a time versus something graph. So I'm going to give you just a few minutes to work on that. You can talk to each other. I'm going to turn the camera off so you can talk without being overheard.